In our previous tutorial, we looked at how to implement matching networks not just by employing capacitors and inductors, but also by using transmission line sections. What we did was inserting a transmission line section in series with our load, and this allowed us to move along a circle of constant radius centered on the Smith chart in a clockwise direction down to the circle of constant conductance where our target impedance lied. We then used a shunt capacitor to move down this constant conductance circle to the exact point that we wanted to get to, which was the impedance we wanted our port to see in place of the load impedance that we had. So in that example, we used a transmission line segment and then a discrete element. In this tutorial, we will be looking at the case when we can implement the whole matching network by using transmission line based elements. As we have seen in the manual, we can implement capacitors and inductors at high frequency with short segments of transmission lines, which are either terminated with a short circuit or with an open circuit. We have seen how transmission line segments, which are less than 90 degrees in terms of electrical length, terminated with a short circuit, behave like an inductor. We have also seen how transmission line segments, which are less than 90 degrees in electrical length and terminated with an open circuit, behave like capacitors. In this tutorial, we will first see how the impedance of such transmission line elements and capacitors and inductors compare, and then we will apply this technique to be able to devise matching networks which are purely based on transmission line segments rather than discrete elements like capacitors and inductors, and this can be very advantageous, particularly at high frequency. So as usual, the first step in the setup of a simulation project is to go to project options. So we'll double click on that and then select our frequency to be 1 GHz and then select single point and apply, and then we'll go to the global units tab and we'll select our conductance to be millisiemens, inductance in nanohenries, capacitance in picofarads. Now we can open a new schematic by going to Circuit Schematics and clicking on New Schematic. We'll call it Open Stub. And the first step in a schematic setup is inserting a measurement port by pressing Ctrl P or clicking on the icon on the top menu. So we'll press Ctrl P and place a port on the schematic. Now we want to insert a transmission line which is terminated with an open circuit. Now we've seen an element which allows us to specify a transmission line segment in terms of its electrical length, and that is called T-lin. In this case, we'd like to have a transmission line which is terminated with an open circuit, and open circuits and short circuits are not straightforward at high frequency. So there are specific elements in Microwave Office which are dedicated to representing such transmission lines which have specific terminations which are not easily implemented. In the case of an open stub, there is an element available which is called TLOC, which is an open circuit transmission line. So what we can do is press Ctrl L, type TLOC, and then here we have it. Double click and place it on the schematic like so. Then connect the element to the port. As we had with T-lin, we have an electrical length here to specify the dimensions of this element, and in order to specify an electrical length you have to specify which frequency this electrical length relates to. In our case this is 1 GHz, so we'll have to change F0 to 1000 MHz. In addition, we'd like to be able to tune the parameters of this element, so we can double click on it, and then of course we've got the properties window that opens up, and we can start by setting an initial value for the length to 0 by making the element tunable, because we'd like to be able to change this value, and then setting some limits for our tuner. We'll decide to go between 0 and 180 degrees in increments of 1 degree, and this will allow us to go all the way around the Smith chart, because as we know, an electrical length of alpha degrees corresponds to traveling around the chart by 2 alpha. So once we've got to 180 degrees for the electrical length of our line, we'll have traveled around the chart by 360 degrees. Click on OK. Then also on this schematic, we'd like to put a capacitor so that we can compare the impedance of the capacitor to the impedance of the open circuited stub, which for electrical lengths of less than 90 degrees is meant to behave like a capacitor. So we'd like to verify this ourselves. Let's press Ctrl P to add a second measurement port, and then let's fetch a capacitor by pressing Ctrl L and type in cap. Place it on the schematic, insert a ground reference, and then connect it to the port. So now from port 1, P1, we can get the reflection coefficient that comes from our open circuited stub. And from the reflection coefficient, we can get the impedance by using a Smith chart. And the reflection coefficient that relates to this port will be S11. For port 2, we can get the reflection coefficient, which then can give us the impedance of the capacitor as seen by the port by being represented on the Smith chart. And of course, the reflection coefficient for port 2 will be S22. Now we'll do a similar thing with the capacitor in terms of its properties. We'll double click on it, and then we'll assign an initial value of 0, and we'll make it tunable, and we'll set the limits for it to be between 0 and 30 picofarads in increments of 0.1 picofarads, and then click on OK. So now we've got a schematic setup which allows us to compare the impedance of an open circuited stub and a capacitor at the frequency that we're working at, which is 1 GHz. So let's right click on the graphs and open a new graph. Of course we need a Smith chart. We'll call it open stub, and then we need to add measurements on this chart. So let's right click, go on to add a new measurement, and then from our schematic open stub we'll get the S11, which is the reflection coefficient of port 1, and by being represented on the Smith chart will give us the impedance of the actual stub. So we'll click on apply, and then we want the impedance of the capacitor, which we can get from the reflection coefficient at port 2. So we get S22 on the chart also. Click on apply and then OK. Now simulate. At the moment you can see that both measurements are on this point on the chart, which represents extremely high impedance. Now if we go back to the schematic, let's try and understand why this is. Well, we've got an electrical length for our open circuited stub of 0 degrees. So effectively what you've got is a port with an open circuit at its terminals. So of course the impedance that it sees is just a very high impedance, virtually infinite. When we look at the capacitor here, we are saying that the capacitance is 0 picofarads. This means that the plates of the capacitor are so small that they can't hold any charge at all. It is very much like each plate is like the end of a wire. And there are these two wire terminations which represent the two plates, which can't really interact with one another because they can't hold any charge, and hence there can't be any displacement current between the two. So for a 0 picofarads capacitor, we assume to have effectively an open circuit. Now let's go back to our Smith chart, and then let's open the tuner. You can see that the values that we've set in the element properties are there. We can tune the capacitor between 0 and 30 picofarads, and we can tune the electrical length of our open circuited stub between 0 and 180. So let's start by tuning the capacitor value. If we increase the value of the capacitor, you can see that we are moving along the outer circle of the chart, and that is because in this case we've got an ideal capacitor, and hence there is absolutely no loss. The impedance of this capacitor is purely imaginary, which means that we just have a reactive component with no loss whatsoever. We can also see that since we're looking at the impedance chart, as we increase the capacitance, we are actually decreasing the impedance in absolute value. And that's because the reactance of a capacitance, which determines entirely its impedance in this case because we are looking at a lossless case, is 1 over omega c, and hence it is inversely proportional to the value of c. Now let's revert to the original value for the capacitor, and now let's tune the length of the transmission line and see what we get. Well, as we start increasing the transmission line length, you can see that we are basically having the same result as we had for the capacitor. So we can see that the stub can really be seen in terms of impedance as a capacitor, and its capacitance changes based on the electrical length that we've chosen for our open circuited stub. Now, however, there is another effect that you can't achieve with a capacitor. With a capacitor, you always stayed in the bottom half of the chart. There was no chance that you could possibly move over to the top half, which would have a positive impedance and hence be inductive. However, here, if we go over 90 degrees, you can see that now we are moving to the top half of the chart, and hence what we are getting effectively is an inductor, an ideal inductor with no loss. So we have to be very careful here. The open circuited stub will only behave as a capacitor as long as its electrical length will be less than 90 degrees. Also notice, and we'll do this with the 90 degrees electrical length because it makes it easier to see, then when the length of your stub is 90 degrees, you've gone around the Smith chart by 180. And remember that this is a very important thing for any transmission line, since the reflection coefficient measures the reflections along a line. Once you've gone to the end of the line and back, you will have traveled twice its length. Now let's revert to the original values for both, and let's see, for example, what kind of length of transmission line we need to achieve a specific value of a capacitor. For example, if I wanted to get a capacitor value of, say, 3.2 picofarads, which was just what we had in the case of our previous matching network. We used a shunt capacitor of 3.2 picofarads in shunt with our transmission line to achieve the match. What would be the value of the electrical length of the open circuited stub that I would need to use to replace the capacitor? We can just use the tuner and see when these 2 points overlap. And you can see that the electrical length that you need to realize such a capacitor is 45 degrees. So we could have replaced the capacitor in that example by an open circuited stub with a 45 degrees electrical length, and this would have allowed us to achieve the match all the same. Of course, this is not the only way to calculate the electrical length of the open circuited stub that you can use to replace your shunt capacitor. Well, since the capacitor was in shunt, our stub will also be in shunt, and we will just need to know what susceptance we want to achieve. In our previous case, we had to achieve a susceptance of 20 millisiemens. So we can use a simple formula to work out the value of the electrical length for our stub, and all we need is the susceptance that we want to achieve and the impedance of the transmission line which we're using for our stub. In our case, we'll be using a transmission line with a 50 ohm characteristic impedance, terminated with an open circuit, of course, and the susceptance is about 20 millisiemens. So we can use the formula shown to work out theta, which is our electrical length, and you can see that the result is pretty much the same as the one that we get with the tuner. Now, why don't we just verify that if we used the stub instead of the capacitor in our previous example, things would have worked just the same? Well, let's close the tuner and do just that. Let's go to Circuit Schematic, open a new schematic, and then we'll call it Stub Match, and we'll place the elements in the schematic which we had in our previous example. So we need to have a port there, which represents a source with an impedance of 10 plus 20J, and then we had a load of 100 plus 50J ohms. So we'll just get an impaired element, place it on the schematic, add a ground reference, and then we'll set R to 100 and the reactance to 50. What we did to achieve a match was to insert a transmission line section, which we can get by searching for T-lin, and we found that the electrical length of this transmission line was 72 degrees at 1 gigahertz. Then we put a capacitor in shunt with this transmission line, place it in shunt with the line, and then connect it to ground. And then we said that the value of this capacitor was 3.2 picofarads. Let's connect our source to our matching network now. And if we've done everything correctly, we should now see a reflection coefficient of 0 from this port here. So let's go back to our graph and let's right click and add a new measurement. And we want to use our stub match schematic, get S11, so we'll just click on apply and then OK. Then simulate. And you can see that we are bang on in the middle of the chart. To make this a bit more obvious, I'll add a marker which allows us to see where we are. We can also denormalize the marker to make things a bit more legible. Let's right click on the chart, go on to properties, and then on the markers tab, and let's choose to denormalize to 50 ohms. Click on apply and then OK. So you can see we're almost at 50 ohms, pretty much there. Now let's go back to our schematic here, and we said that equivalently to this capacitor, we could use an open circuited transmission line stub to achieve the same effect. Well, let's see if this is true. Let's remove the capacitor, and then let's pull up using Ctrl L and type in TLOC, an open circuited stub, and place it in parallel with a transmission line. Now remember that we need to specify F naught, and in our case it's 1000 megahertz or 1 gigahertz, and we said that the electrical length we need to achieve a capacitor of 3.2 picofarads is 45 degrees. So the moment of truth, let's simulate and then look at our graph yet again. And you can see that we are right bang on in the middle of the chart. In fact, we even have a slightly better match than before. So we've seen how a capacitor can be replaced by an open circuited stub. But what happens in the case of inductors? Can we replace those with a transmission line element? As it turns out, we can. We can use a short-circuited stub to achieve a similar match between the inductor and a transmission line segment. So let's go back to our circuit schematics, and we can duplicate the open stub schematic by right-clicking and selecting Duplicate Schematic, or by simply clicking on it and dragging it onto the circuit schematics heading. And then we can rename it, and we'll call it Shorted Stub. Now what we need to do is replace our open circuited stretch transmission line by a short-circuited transmission line. And again, Microwave Office has got a specific element to do this, which is called TLSC. Now we can just delete this element here, and then press Ctrl L and search for an element called TLSC. And then place it on the schematic like so, and connect it to the port. Same rules apply in terms of its setup. We have to select the right frequency of operation, which is 1 gigahertz, so 1000 megahertz. And then we need to set up some of its properties to be able to tune it and see what happens as we change its electrical length. So let's double click on it and start with a length of 0 degrees, make it tunable, enable some limits and go between 0 and 180 degrees in increments of 1 degree. Click on OK. And then we can go down to the other bit of the schematic and replace our capacitor with an inductor. So let's just remove this and then get ourselves an inductor. Place it on the schematic and then connect it to the port. Now we need to double click on this element as well and change some of its properties. We'll start with a value of 0 for our inductor, we'll make it tunable, and we'll set some limits for it, say between 0 and 30 nanohenries in increments of 0.1 nanohenries. And then click on OK. Now let's right click on graphs, select new graph. Again we want a Smith chart, and we'll call it Shorted Stub. Then we'll right click on the chart, go on to add a new measurement, and we'll get the S11, but this time it'll come from the Shorted Stub schematic. And S11 is the reflection coefficient at port 1, which will give us the impedance of the short-circuited stub. Click on Apply, and then we need the impedance for our inductor to be displayed on the chart, and that will come from the reflection coefficient at port 2, which is S22. Click on Apply, and then OK. Now simulate. You can see that in this case we start from a different point on the chart, the point which represents a 0 impedance. Let's go back to our schematic and see why that is. The electrical length of our transmission line is 0. So effectively what we're doing is connecting the port to ground, short-circuiting the port, and hence the port sees an incredibly low impedance, which is 0. When it comes to the inductor, for an inductance of 0 nanohenries, that means that there is no back EMF due to the current flow, and hence the current can flow freely down to ground, and our port sees a very low impedance. Now let's go back to our graph, and let's open the tuner. And you can see that yet again you can tune both the inductor and the electrical length of your short-circuited stub much in the same way as we did for our open-circuited stub and our capacitor. So if I start increasing the inductance of my inductor, you can see that I'm traveling around the outer circle of the Smith chart, and that is because we have an ideal inductor whose impedance is purely reactive, and hence we have no loss at all, since there are no resistive elements, parasitic elements for the inductor. And you can also see that as I increase my inductance, I also increase the value of the impedance. And that is because the impedance of the inductor is entirely due to its reactance, which is omega L. Now I can revert the value to its initial value, and then I can start tuning my short-circuiting transmission line a little bit in terms of its electrical length. So if I increase its electrical length, you can see that I'm achieving the same thing that I was achieving by increasing the inductance of my inductor. So effectively, I've got an inductor here, which can be used to replace my discrete inductor. Now, if I carry on increasing this electrical length, you see that I get to a point where I've gone around the chart by about 90 degrees. And notice how, again, we've got a transmission line length of 90 degrees, but we've traveled 180 on the chart. And you can see that if I carry on increasing the length of this line beyond 90 degrees, I get to the bottom half of the impedance chart, which means that effectively I've created a capacitor. So the big difference is here, as before, that when you have a transmission line, either short-circuited or open-circuited, to represent either a capacitor or an inductor, whereas the impedance of the capacitor will be always in the bottom half of the chart, and that of the inductor always on the top half, when you're using an open-circuited or short-circuited stub, depending on the electrical length that you're using for them, you could have either an inductor or a capacitor. However, the usual way things are done is to keep the transmission line length to less than 90 degrees and use an open-circuited stub to create a capacitor and a short-circuited stub to create an inductor. Again, we could pick a value for the inductor and then try to find the electrical length needed for our transmission line short-circuited stub to be able to have the same impedance of the inductor. So let's say that we choose something like 6 nanohenries. Then we can start tuning the electrical length of our short-circuited stub until the 2 points overlap. And you can see that this happens when we have an electrical length for a short-circuited stub of about 37 degrees. Again, we can use a formula to calculate the length of our transmission line stub. Again, since these elements are usually added in shunt, we will need the susceptance that we want to achieve, so the susceptance that corresponds to the shunt inductor that we want to add, and then we'll also need the characteristic impedance of the transmission line, which we've kept the same throughout, and of course in this case would be 50 ohms, to work out the electrical length, theta, of our short-circuited stub needed to achieve the shunt inductance that we want to get to achieve our match. So now that we've done all this and we've shown the equivalence of capacitors and inductors to open-circuited and short-circuited stubs, we can just get rid of all this stuff and start afresh and carry out a match which will be entirely implemented in terms of transmission line segments and transmission line stubs. So let's close the tuner, get rid of all of our schematics, and then of our graphs as well. So all we've got left is our project options, and we can start afresh. So let's open a new schematic, and let's call it TX line match. And then the first thing that we'll put on, as usual, is a measurement port. Press Ctrl P and insert the port here. In this case, we'll carry out a match between a resistive port, which has got an impedance of 50 ohms, and a load which has got a complex impedance. This is nothing but a special case of two complex impedances, and there will be no loss in generality in doing the match this way. Also, it is quite a usual thing that we have to match a complex termination to a 50 ohm source. So it is quite an instructive case. So let's suppose that we've got a source with a 50 ohm internal impedance, and then we've got a load which comprises of a resistor with a resistance of 100 ohms in series with an inductor with an inductance of 8 nanohenries. So let's get a ground reference here, and then we'll connect the port to the load. So let's open a new graph, and of course our graph will be a Smith chart, and let's call it TX line match. Then right-click on the chart and add a new measurement, and of course we'll get an S11 measurement from our schematic to be able to see the impedance that the port is currently seeing. Click on Apply and then OK, then Simulate. So we've got our impedance right here, and the place that we want to get to is the center of the chart, which represents 50 ohms and is the impedance of our source. So let's add a marker by pressing Ctrl M and then clicking on this point here. And we'll also denormalize it by right-clicking, going on to Properties, and then on the Markers tab, selecting Denormalize to 50 ohms. Click on Apply, and then OK. So you can see the actual impedance in mathematical form of our series RL with a 100 ohm resistor and an 8 nanohenry inductor, which has got a reactance of about 50 ohm. So before we carry on, as usual, let's change the appearance of our chart to include both impedance and admittance grids, and also to reduce the density of the lines. So let's right-click, go on to Properties, and then on the Grid tab, select to have both admittance and impedance grids visible and take off the values. Then on the contour density, select Coarse. Go to the Format tab, select green for the impedance lines and red for the admittance lines, and then click on Apply, and then OK. Now, as you can see, things are more legible and not quite as busy. To go from our start point, which is here, to the end point, which is the center of the chart, we could, if we wanted to, use any L section, pi section or T section, but this time we'll do it differently. We'll do it purely with transmission line segments. So the first thing we need to do, as we did in the previous example, is go back to our schematic and then add a transmission line in series with our load. So let's just remove this connection here and then press Ctrl L, type TILIN in the search box and fetch our transmission line specified in terms of its electrical length and place it in series with our load. Again, we need to specify the frequency we're operating at, which is 1000 MHz, and then its electrical length we just need to make tunable. To do this, we can double click on the element and we'll select an initial electrical length of 0, then we'll make it tunable and we will enable some limits for it, going between 0 and 180 degrees in a step of 1 degree. Click on OK, and now we are ready to tune our transmission line length to take us to a convenient place on the Smith chart from which we can then reach our target point. So let's go back to the graph, let's open the tuner, and then let's simulate. You can see that we haven't moved at all, and that's because the transmission line length is 0, so effectively we haven't got anything there interposed between our source and our load. However, what we can do is increase the length of the line at this point to be able to get to a point from where we can easily reach with one additional element our target impedance, which is 50 ohms, and it's the center of the chart. We know that if we increase the length of our transmission line, we will be moving clockwise around a circle of constant radius, which is centered on the center of the chart. Now, this circle of constant radius will intersect the unity constant resistance circle, which is a circle on which our target impedance lies, in 2 points, one in the bottom half of the chart and the other in the top half of the chart. And also this circle that is described by increasing the transmission line length will also yield 2 intersections with the constant conductance circle, one at the bottom and one at the top. And when we are on this circle, we can also easily reach our target impedance, which happens to be on it. So let's start increasing our transmission line length and see what happens. As we increase it, we are moving around clockwise, and then we get to our first intersection, which is the intersection with the unity constant resistance circle. Now, from here, we could easily move up to the center of the chart, which is our target point. And how do we move up? Well, we know that if we move up a constant resistance circle, we are actually adding a series inductor. So we could add a series inductor and go up here. However, we want an element in shunt because it is not easy to realize series transmission lines to do this sort of thing. So what we usually do is add a stretcher transmission line in series with the load to get a circle of constant conductance, and then from there we can add a shunt element. So great that we got here, we had the option, we could have the transmission line of 45 degrees length and then add an inductor in series to get to a point, but we want to use transmission line elements, in particular parallel stubs. So we need to carry on increasing the length of our transmission line until we get to a constant conductance circle. Let's move the marker readout away a little bit, and now from here we could use a shunt inductor to go up the constant conductance circle to our target point. And to implement this shunt inductor, we have the option of using a short-circuited stub, as we saw previously. So from this point, I could easily just use a short-circuited stub of the appropriate length to get to the center of the chart. So what I've done here is add a transmission line of an electrical length of 72 degrees in series with my load. This has taken me to a circle of constant conductance. From here I can add a shunt stub, a short-circuited shunt stub, to realize an inductor and then move up the constant conductance circle to the center of the chart. But what is the electrical length of this shunt stub? Well, first of all, because we are adding an element in shunt, we need to change our marker readout to admittance. So right-click on the chart, go on to Properties, and then on the Markers tab, choose the readout to be in terms of admittance. Click on Apply, and then OK. So the difference in susceptance between my target point and my current point is 20 millisiemens, and I can use the formula to work out the electrical length of the short-circuited transmission line stub needed to achieve a susceptance of 20 millisiemens. And this turns out to be 45 degrees. So now, if I close the tuner and go back to my schematic and add a short-circuited stub in parallel with my transmission line segment, I should be able to see a perfect match between source and load. So let's make a little bit of space here and then press Ctrl L and fetch a TLSC element, so a short-circuited transmission line stub, and then you can place it right here in shunt with the transmission line segment that you've already added. And we said that we want an electrical length of 45 degrees at a frequency of 1 GHz. Now let's click on Simulate and go back to our graph, and you can see that we're bang on in the middle of the chart. Now let's remove the element that we've just added, and this will take us back to where we were before. If I open the tuner yet again, you can see that there are two other points that I can reach, from which I can then use another simple element to get to the target point. I could move up the chart a little bit further, up to an electrical length of 135 degrees, and then if I just move the marker readout away a little bit, I'm back on the unity constant conductance circle, and from the point that I've reached, I can just add a shunt capacitor to move down the constant conductance circle to the center of my chart. Of course, instead of using a capacitor, I could equivalently use an open-circuited stub, as we've seen. And to work out the length of the stub that we need, we just need to look at the susceptance that we need to add. And in this case, as in the case of the point that we had in the bottom half of the chart, the susceptance that we need is 20 millisiemens. So now we can use the formula for open-circuited stubs, which allows us to work out the electrical length needed to achieve a specific value of the susceptance. As you can see in the formula, all I need is my transmission line characteristic impedance, which is 50 ohm for us, and the susceptance that I want to achieve. And surprise, surprise, this value turns out to be 45 degrees. So what I need to get to be able to achieve a match is an open-circuited transmission line stub with an electrical length of 45 degrees. So let's close the tuner and go back to our schematic, and you can see that in this case the transmission line that's in series with the load has got an electrical length of 135 degrees as opposed to 72 as before. Now I need to add an open-circuited stub in the same place where I added my short-circuited one earlier. So let's press Ctrl L and fetch an element called TLOC, and then we'll put it in shunt with our transmission line segment. We want an electrical length of 45 degrees at our frequency of interest, which is 1000 MHz. Now we click on Simulate and we go back to our schematic, and yet again we are bang on in the center of the Smith chart, which is the point we wanted to be at. Now lastly, I'm going to go back to the schematic and delete this shunt stub, click on Simulate, so that on my chart I will be back to the point where I was before inserting the open-circuited shunt stub. And I'll open the tuner again and show you that if I increase my transmission line length further, I get to a point here from where I could just insert a series capacitor to get to the center of the chart. As we said, we won't be looking at series elements here because we want to use transmission line elements, and those can easily be added in shunt, but when you try and do things by inserting series elements like that, things get a bit more complex. So let's go back to the start. So we started from this point here, and we've shown that we can insert a transmission line segment in series with our load, which will take us around the chart on a constant radius circle. So we can add a transmission line length, which is equal to 45 degrees, and then add a series inductor, or add a transmission line length, which is equal to 72 degrees. And then from here, we can either add a shunt inductor or a short-circuited parallel stub. Also, we can insert a transmission line length in series with a load of 135 degrees, and then we can either add a shunt capacitor or equivalently an open-circuited transmission line stub in parallel with our transmission line. Or we can go even further and have a transmission line with a length of about 161, maybe even 162 degrees, and then add a series capacitor to get to our target point. So now you might ask whether we could use the IMatch Wizard, which we looked at briefly last time, to carry out this type of match. And as it turns out, you can. Let's go to the Project tab and click on the plus next to Wizards to expand them. Then pick the iFilter Wizard and double-click on it. You can see that the usual window opens up, which allows you to select a matching network at the top. So click on Matching Network, and then select Bandpass and Impedance Matching Network. Then click on OK, and you get given the choice of your source and load impedance. Our source impedance will be of a resistive type, so we keep it to RES, and its value is 50 ohms. And our load impedance is different. It's a series RL, where the resistance is 100 ohms, as we've seen, with an inductance of 8 nanohenries. So we set our two terminations, our source and our load. Click on OK, and then you can select transmission line plus stub as the type of matching network that you would like to use. So click on that. Make sure that you've got the right frequency selected up here, which is right for now, 1000 megahertz. And then also select the spot frequency mode from here. Now you can see that the first element is a shunt open-circuited stub plus a transmission line. And this is shown in the graph here. So you've got a shunt open-circuited transmission line stub, and we have a transmission line in series with our load. And look at this, the values for these elements are exactly the same as the ones that we calculated. So we've got a 45 degrees length for our transmission line stub, which has got a characteristic impedance of 50. And also we've got a length for our stretcher transmission line, which is in series with the load, of 135 degrees. And its characteristic impedance is also 50. You can also see on the Smith chart here what path was followed to achieve this match. Now we can compare this matching network, which comprises of an open-circuited stub and a transmission line, to its equivalent, which would have a shunt capacitor and a transmission line. So let's just click on that and see what we get. You can see that we get exactly the same length of line and a capacitor of about 3.2 picofarads. So the two networks really are quite similar. You can have one or the other. And in this case, the path that was used on the Smith chart to get from one point to the other is shown correctly. This is what you should be seeing for both shunt capacitor plus transmission line, and also for open-circuited stub plus transmission line. Now let's have a look at the other configuration that we can have, and that is a shunt short-circuited stub plus a transmission line. Now look at this yet again. We've got a short-circuited stub here, which has got a length of about 45 degrees, and we have a transmission line in series with our load, which is about 72 degrees. That's exactly what we did. And you can see that, of course, the characteristic impedance of both stub and transmission line are the same and are 50 ohms. You can also see on the Smith chart that the path that was followed from our load to our source to find the matching network was exactly the same as the one that we followed. Now, as we know, a short-circuited stub and an inductor should be pretty much equivalent. So if I click on the shunt inductor plus TL type, I should get a transmission line length which is exactly the same for the transmission line in series with the load, and then a shunt inductor which will have the same susceptance as the short-circuited stub. And it turns out to be about a nanohenries. You can also see that the path followed on the Smith chart is exactly identical for both the short-circuited stub and the shunt inductor options. The other two options that we've got here are the ones that we saw possible on the Smith chart, and those were the ones where we had a transmission line length plus a series element. So we can have a transmission line with a series inductor, and you can see that this again works the same way as we've shown on our Smith chart, and the transmission line length is about 45 degrees and the inductor about a nanohenries. And then if you do it with a capacitor, you go again further around the chart, and then you add a capacitor in series, and the transmission line length is more or less the same as we worked out, and the value of the capacitor we didn't work out, but this is what it turns out to be. Now, lastly, I'd like to have a look at the frequency response of these matching networks. What I'm going to do is to use this button here to be able to display the frequency plot a bit more clearly. So I'll just click on it once to make the graph appear a little bit bigger. Let's start with the transmission line plus the shunt open circuited stub, and then let's increase the span of our frequency response. Now you can see an interesting effect here. Of course, the return loss, the S11, will be minimum at the frequency that you aimed for at 1 GHz. And that is because obviously you designed to have a very low reflection coefficient at the frequency of interest so as to have maximum power transfer to the load. However, on the insertion loss, you can see that although at 1 GHz your insertion loss is very low, and this is what you want, when you go up to twice your frequency, all of a sudden the insertion loss drops dramatically. This means that basically you're getting effectively no power transferred to the load at all. But why is that? Well, let's have a look at our circuit down here. So this is an open circuited stub. It means that we've got a section of transmission line here which is 45 degrees in its electrical length, and then we've got an open circuit at the end of it. Now the electrical length is proportional to frequency, and when I double the frequency, I double the electrical length of my stub. So at 2 GHz, this stub will look like a transmission line of an electrical length of 90 degrees, at the end of which we've got an open circuit. Now remember, we looked at this in the manual. When you have a transmission line which is 90 degrees in electrical length, you have the quarter wave transformer effect. And that means that you effectively flip a point on the chart by 180 degrees. So if we had an open circuit at one end of our quarter wave line, at the other end we will see a short circuit. So at 2 GHz we will effectively see a short circuit here, and hence all the power coming from our source will try to go down this low impedance path but find a short circuit, and hence will be mostly reflected, thereby making the value of S21 really low and the value of S11 really quite high. So that's why we've got this dip here, this huge trough in the S21. Let's now look at the case of the transmission line with the shunt short-circuited stub. You can see that in this case, again, we have a fantastically low return loss for our frequency of interest, but you can also see that your S21, so your insertion loss, is pretty constant across the band, and we don't have the same effect as we had before. And now you may say, well, yes, but the stubs are the same length, they're both 45 degrees. Okay, one is open circuited and one is short circuited, but what happens at 2 GHz with this one then? Don't you have any trouble? Well, again, let's reason this out. We have a stub which is 45 degrees in electrical length at 1 GHz, and there is a short circuit at the end of it. Now, when we go to 2 GHz, the length of the stub will be effectively 90 degrees, and hence we will have a quarter wave line, but this time, at the end of this quarter wave line, we have a short circuit, not an open circuit. So we will transform a short circuit into its opposite, which is an open circuit. So at this point here, we will see an open circuit. And an open circuit is no trouble at all, because this just means that there's going to be no power that goes down here at 2 GHz. This is going to appear like it doesn't exist effectively, and all the power is just going to go through. Now, feel free to play around with this wizard. It's extremely useful and very helpful, but it is also important to understand where it comes from and how you do things manually, so that you don't just blindly click on various things until you achieve what you want to achieve.